Okay, so we're starting chapter 5, which is our analytical trig unit. And so the first lesson here is the fundamental identities. And so we know our reciprocal identities. Remember, we know that cosecant is a reciprocal of sine, so we can say that cosecant is equal to 1 over sine of theta. And then vice versa, the reciprocal of sine of theta is cosecant of theta, so we can say the sine of theta is equal to cosecant of theta. Secant's reciprocal is cosine. So secant of theta is equal to 1 over cosine of theta. And cosine of theta is equal to 1 over secant of theta. And then cotangent's reciprocal is tangent. So cotangent of theta is equal to 1 over tangent of theta. And tangent of theta would be equal to 1 over cotangent of theta. Now our quotient identities. So think back to when we talked about x, y, and r. And remember, tangent was y over x. Well, on my unit circle, remember y is our sine value, and x is our cosine value. So we can say that tangent is equal to tangent of theta is equal to sine of theta over cosine of theta. And then, of course, cotangent of theta is its reciprocal, or we could say that it's x over y. And so we know that x was our cosine, y is our sine, and so we can say that cotangent of theta is equal to cosine of theta over sine of theta. Then we have our Pythagorean identities. And so Pythagorean identities, when I hear that, it makes me think about the Pythagorean Theorem, which is where it comes from. So remember, the Pythagorean Theorem says a squared plus b squared equals c squared. But we know on our unit circle, remember we've been using this, but we didn't call them a, b, and c. We said it was x squared plus y squared equals r squared. Well, on our unit circle, which of our trig functions represents our x's? Remember, that's cosine. So we could say, well, this is cosine squared of theta plus the trig function that represents our y's on our unit circle is sine. So this is sine squared of theta equals, and on our unit circle, our radius, our r, is 1. And so 1 squared is 1. So this is our first Pythagorean identity that you'll put up on that first line up above there. Now the next two lines are just manipulations of this equation here. So we start out with the cosine squared of theta plus sine squared of theta equals 1. Now remember, whatever I do to one side of the equation, as long as I do it to the other side of the equation, it makes it true. And what I do to one term, I have to do to all terms. So what if I end up taking all of these and I divide them all by cosine squared? So when I do that, I get 1 plus sine squared over cosine squared. Well, sine over cosine is tangent, so sine squared over cosine squared is going to be tangent squared equals 1 over cosine squared of theta. Well, 1 over cosine is secant, so 1 over cosine squared is going to be secant squared of theta. And so here is our second Pythagorean identity. And then what if I do the same thing, but this time I'm going to divide them all by sine squared. So let me get this written out. Okay, and we're going to divide both sides, or all three terms, by sine squared of theta. All right, well, we know that cosine squared over sine squared is cotangent squared, plus sine squared divided by itself is 1, equals 1 over sine squared, then is cosecant squared. And there is our third Pythagorean identity. So that will go on the third line above. All right, so there's the three Pythagorean identities, and now we can manipulate these, okay? So like we could solve that first one that we did, we could solve it for just cosine squared, or we could solve it for sine squared. Or we could get cosine squared and 1 on the same side of the equation and move the sine squared to the other side. Or we could get the sine squared and the 1 on the same side of the equation and move the cosine squared to the other side. You know, there's all different types of algebraic manipulations that we can use on them to come up with all different types of formulas. All right, so example 2 here, it says to use a quotient identity to simplify and rewrite. So remember, to simplify means we want to make this smaller. So our goal is to make this as small as possible. And so we really want to try to get down to where it's just one term. Now sometimes you may not be able to, but a lot of times you can. So our goal is to make this as small as possible using every identity we can to get there. So they gave us a clue here. They told us to use the quotient identity. Well, even if they hadn't told us that, guys, and we'll talk more about this in 5.2, one of the things that I always do is if I don't know what else to do, I change everything to sine and cosine. So if I do that, this cosine, now that's beta, that's just like x or theta or y or z. It's just a variable of the Greek alphabet, okay? So this is already in cosine. But we know that tangent, remember, is sine over cosine. So it's going to be sine of beta over cosine of beta. Now, we know that this fraction then would be over 1, and when we multiply fractions, we multiply straight across. So, but also remember, anything that's on top and bottom will cancel. So I'm left with sine of beta over 1, which I need to just simplify as sine of beta. All right, for B, I'm going to do the same thing. I'm going to go ahead and change everything to sine and cosine. So we know that secant is 1 over cosine. We know cotangent is cosine over sine. And then sine of x, well, that's just sine of x over 1 then. So remember, anything that's on top and bottom will cancel. So my cosines will cancel. My sines will cancel. So I'm left with 1 over 1, which is just 1. Example 3 talks about the idea of decomposing fractions to simplify and rewrite them. And so there's two different ways a lot of times we'll work A. But the big thing here is don't forget, dividing by sine is the same as multiplying by its reciprocal. So this sine would be like sine over 1. So I could rewrite this then as cosecant of theta times that reciprocal, which is 1 over sine of theta. And then we know that, let's see, 1 over sine of theta is cosecant of theta, and cosecant times cosecant then would be cosecant squared of theta. Now, if you had changed the cosecant to 1 over sine, you just get 1 over sine squared of theta, but you know that 1 over sine is cosecant, and that's a simpler version than 1 over sine, okay? Now, the other way that you could have looked at this one, and this is what you'll do a lot when you're working some of the problems, is you'll say, okay, well, let's take it all to sine and cosine, and so I know that cosecant is 1 over sine, and then it was all over sine. Now, be really careful here, guys, because you got a lot of letters going on that you'll get confused on which one is your little fraction versus which one was your original fraction line. If you notice, all the time I draw my original fraction line longer than the other one. So I know this is my little fraction. That's what I'm having issues with when I have a fraction within a fraction. Okay, so what I'm going to do then is I need to get rid of that little fraction. In order to do that, I'm just going to multiply by its denominator. So I'm going to multiply the whole top of my big fraction by sine of theta. What you do to the top, you have to do to the bottom. So we do this on top. That gets rid of that little fraction. So we get 1 over, and then sine times sine is sine squared of theta. And then remember, 1 over sine of theta is cosecant. So 1 over sine squared would be cosecant squared of theta. So either way, we got the same answer. It's just which way do you see it? All right, on B. Now on B, we possibly could work out this numerator, okay? We could subtract them and make them one fraction so that it looks like what we did on the second part of A there, okay? And be able to work it out from there. But another way is, don't forget that when you have a fraction that has a plus or minus sign on top, the denominator was a common denominator for each of those individual terms. So what that means is this cosecant of x here was the denominator for the sine of x at one time. And then it was a minus sign because of the minus sign in the middle. And that cosecant of x on bottom was also the denominator for the cosecant of x that was on top. So it was that common denominator. Because remember, if I want to go backwards now, I would combine these two over the common denominator, and that's what we started with. And so from there, I can work this out. So let's see. Depends on how you want to do the first one. I'm going to go ahead and do it like I see most students do it. I'm going to change cosecant of x to 1 over sine of x. So notice again, I made sure my divide lines are different, so I know this is my little fraction, okay? And so I'm going to multiply the top and bottom by sine. And I end up with sine squared of x over 1, which we know is just sine squared of x. Now, I'm going to work on the next part, minus, well, cosecant of x divided by itself is just 1. So minus 1, minus 1. Now, something to watch out for. This just said to use the idea of decomposing the fractions to simplify and rewrite. So it didn't tell me to factor, okay, because this has two different ways we can go. One, factoring, which we're going to talk about in the next section, this is a difference of squares, so we could factor it out. Two is anytime I see something with a squared and a 1, it makes me think about my Pythagorean identities, okay? So I'm going to look back and see, is there a Pythagorean identity that has a sine squared and a 1 in it? And you should answer, yes, there is. The very first one that we looked at. So cosine squared of theta plus sine squared of theta equals 1. Can I get sine squared and 1 on the same side with the exact same signs that are in this problem? Well, when I look at this, I want this sine squared to be positive. It's positive where it's at, so I am not going to move it. But I also need this 1 to be on the same side. So let's get the 1 over to the other side. So when I do this, I have this cosine squared of theta plus sine squared of theta minus 1 equals 0. So let's check out what we've got right there. We have a positive sine squared of theta, just like what I needed. We have a minus 1, just like I needed. The only problem is I have this cosine squared still here. So let's move it over to the other side. So let's subtract it. And so we got sine squared of theta minus 1 equals negative cosine squared of theta. This is exactly the same that's in my problem. What is it equal to? It's equal to the negative cosine squared of, I'm going to use x because that's what's in this problem. So there is our answer. One term is simpler than two. All right, so I had to algebraically manipulate that first Pythagorean identity to get my sine squared minus 1 together. And then remember, if two things are equal, you can substitute them. Since sine squared of theta minus 1 was equal to the negative cosine squared of theta, I just went ahead and substituted into my problem into my answer. All right, let's look at 4. It wants us to remember our rules of factoring. And I know it's been a little bit since we did some factoring, so we're going to go back over it. But look at A. A has 3 terms. Well, first, before we even start that, let me back up. Remember the rules of factoring. The first thing you should always look for is your greatest common factor. All right? Then my next thing is I'll count the number of terms. If there are 2 terms, then I remember my options are a difference of squares or a sum or difference of cubes. If there's 3 terms, then my options are either it's a simple trinomial where I just start opening my parentheses, or it's the one that has a number in front of the x squared, and therefore I have to multiply the first times the last, factor that simple trinomial out, and then don't forget to divide it back out at the end. All right, and if there are 4 terms, we factor by grouping. So the first thing we really need to look for in every one of these is, does it have a greatest common factor? So when I look at A, this has a 2 sine squared, a 3 sine, and a 1. The numbers 2, 3, and 1 aren't divisible by anything other than 1, so no greatest common factor there. And they don't all have some type of a form of sine in it. So no greatest common factor there, okay? So how many terms are there? There's 3. So this is a trinomial, and it's one of them that has a number in front. So we're going to do that first times the last. Now, also make sure, though, because we didn't have to worry about this so much before because it was obvious to us, make sure these are the same type of trig function, okay? They both have to be a sine. They both have to be a cosine. They both have to be tangent. They can't be one tangent, one cotangent, okay? They have to be the same trig function. Granted, one of them is squared and one of them isn't. Now, we can also use some substitution here, okay? Since these are the same type of trig function, I just noticed the first one's squared, the second one's not. So I could rewrite this. This is the same as saying 2x squared minus 3x plus 1. If I switch my if I let x just represent sine of x. In that case, most of y'all remember how to factor this. You're going to take your first times your last. And so you have x squared minus 3x plus 2, because remember they multiply. You're going to factor this simple trinomial out. We're just going to do FOIL backwards. Remember your first two terms have to multiply to give you x squared, which are x and x. Your last two terms here have to multiply to give you the 2 and read it backwards. They need to add to give you 3, which is 2 and 1. You need a negative 3, so it's going to be a negative 2, negative 1. Don't forget you multiplied at the beginning by this 2, so you got to bring it back. So we're going to simplify this if possible, the fraction. If not, you throw the number on bottom in front of the x. 2 over 2 does reduce to 1, but 1 over 2 in the next one doesn't reduce at all. If it reduced, I would need to, and then whatever number's on bottom goes back in front of the x. Guys, you have to do that step when we're factoring. I know that when you first learned to factor last year, you were solving the equation, so it didn't matter if you didn't change it because your answer would come out the same. If you're leaving it as a factor like what we're doing, factors don't have fractions, okay? So you cannot have a fraction in your factor. So this is my 2x squared minus 3x plus 1 factored out. The only thing is I didn't have x in my problem, I had sine of x. And so I'm going to go and plug that back in now. So I've got sine of x minus 1 times 2 sine of x minus 1. And that is our factored form. All right, so for B, let's check it. Do we have a greatest common factor? Well, we have a 16 and a secant squared. We do not. We count the number of terms. There's only 2 terms, which means it could be a difference of squares or a sum or difference of cubes. Well, I see a squared in there, so I'm thinking it's a difference of squares. Now remember, difference of squares had this formula. If you're given the problem where like a squared minus b squared, they both have square roots that are nice and pretty. You can rewrite it as the square root of the a squared plus b, or plus the square root of the b squared, and then same thing but with a minus sign, okay? Remember, a and b come from taking the square root of the pieces of the problem, the terms in the problem. So does 16 have a square root? 4. Does secant squared have a square root? Secant. So that's my a and my b. So when I go to plug this in, I got 4 plus secant of x and 4 minus secant of x. Remember, the 16 was first, so the square root of the 16 is going to go first. The secant squared was second, so its square root goes second in the parentheses. Order matters, guys, because of the one with the minus sign. If you try to change it up, it'll give you a different answer. Make sure you can't factor those any further, which we cannot. And so there is our factored form. So C. Remember, first thing is greatest common factor, so let's check. We have a cosecant of alpha. Alpha, again, is like beta, theta, x, y, z. It's just a variable, okay? So we got cosecant of alpha, and then we got cosecant of alpha, cosine squared of alpha. Well, I notice both of those have a cosecant of alpha in it. So we're going to greatest common factor that. We're going to take that out. So we got cosecant of alpha times. Now, when you take it out, you're doing the opposite distributing. Remember, distribute, we multiply it through. Factoring, we divide it out. So I'm going to divide both of these terms by that cosecant of alpha. So it leaves me with 1 minus, those cancel as well, so I have cosine squared of alpha. Now be careful here because, again, we do have a 1 and we have a trig function squared. So we could go back to our Pythagorean identities, and it actually does work out, except the directions here tell me to factor. And so that is also a difference of squares. So I'm going to bring down this cosecant of alpha. It's just part of my answer. And then I'm going to factor the parenthesis here just like what we did in B. It's a difference of squares. What's the square root of 1? 1. What's the square root of cosine squared? Cosine of alpha. So there's my A and my B. So remember, 1 plus cosine of alpha times 1 minus cosine of alpha. And then we can't factor either of those any further, so this is our completely factored form. And then D. The thing is, though, be careful on D because I automatically notice they both start with a C, but these are two totally different trig functions, aren't they? I can't factor them until I can change one of them into the other. So either I need to take that cosecant squared and make it a cotangent squared somehow, or I need to take cotangent and make it a cosecant. Well, there's nothing in any of our things that relate cotangent with cosecant. But there is something that relates cosecant squared with cotangent squared. We have that Pythagorean identity that says that 1 plus cotangent squared equals cosecant squared. Okay? So we can already see that cosecant squared is equal to 1 plus cotangent squared. So where I have a cosecant squared here, I'm going to plug in 1 plus cotangent squared for it. And then I'm going to bring the rest of it here down. All right. Now I don't really need the parentheses there. I just did it so you could see that this was equal to this. So I substituted them in. So I'm going to go ahead and drop my parentheses. So 1 plus cotangent squared of beta minus cotangent of beta minus 3. Well, we have like terms, so let's go ahead and take care of that. And I'm going to write this in descending order of my exponents. So we got cotangent squared of beta minus cotangent of beta minus 2. And so from there, I'm going to check it. There's no greatest common factor. We have 3 terms, so it's a trinomial, and it's one of the simple ones. There's just a 1 in front. So if you need to, remember, change it back. So this is the same as saying x squared minus x minus 2. So when I go to factor that, remember your first 2 terms here, we're going to have to multiply to give you that x squared. So x and x. Your last 2 terms here are going to have to factor to give you 2, but they also need to subtract to give you the 1 right there. So it's going to be 2 and 1. We need it to be a negative 1, so it's going to be a minus 2 and a plus 1. All right, we didn't divide anything out. We didn't multiply anything out, so there's nothing to divide by. So we just got to switch it back now. Our trig function was dealing with cotangents. So we know that this is cotangent of beta minus 2 times cotangent of beta plus 1. And so there is our factored form because we can't factor any further. All right, so example 5 just wants us to simplify. Guys, there's no one direct route to get to your answer. There's lots of different routes. Some are shorter than others. So just see what you can do, if nothing else. Now, so for starters, though, notice that secant of x plus 1 and the secant of x minus 1. Those are not going to be anything with the Pythagorean identities. The reason is to have the Pythagorean identity, it has to have a square, okay? I know that when we use the reciprocal identities and when we use the quotient identities, we were able to take it from unsquared to squared and go back and forth. Because Pythagorean identities come from that Pythagorean theorem, which has a squared plus b squared equals c squared. They have to have the square on the trig function in order to work. So the fact that secant of x plus 1 or secant of x minus 1 doesn't have a square, that tells me not to even worry about my Pythagorean identities. All right, so what else could we do? There is a way we could change secant to 1 over cosine, but then I'm still going to be multiplying. Well, first then I'd have to add, and then I could multiply, and that's a lot of steps. So maybe there's something else I can do. But remember, we just saw that when we had a plus or minus in our answer earlier, that came from that difference of squares. So maybe there's a way I could just work this out. So let's try that. All right, so let's multiply these then. So if I do my FOIL, I'm going to take secant times secant, which is secant squared. Secant times negative 1 is negative secant. 1 times secant is positive secant. And then 1 times negative 1 is negative 1. All right, over, and I'm just going to leave sine squared as it is. If I need to change it, I'll just have to do it later. All right, so I'm going to simplify that numerator. So let's see, we have secant squared of x. Our secant of x plus secant of x cancels, and we have minus 1 over sine squared of x. Now, secant squared of x minus 1. Now it's squared, so, and my instructions is just to simplify. So what does secant squared of x minus 1 equal? Well, remember, if it's a trig function squared and a 1, I'm thinking Pythagorean identities. So I'm looking at the one that has secant squared. Let's see, it tells me that tangent squared of theta plus 1 is equal to secant squared of theta. Okay, well, let's see if we can algebraically manipulate this and make it look like what we've got. So we have a positive secant squared. My secant squared is already positive where it's at. Don't move it. So I need the 1 on the same side, so let's move that 1 over. So it gives me tangent squared of theta equals secant squared of theta minus 1. Let's check. Is that the same exact thing that's in my problem? It is. That means I can replace it with what it's equal to, which is tangent squared of theta. So I'm going to change this to tangent squared of theta over that sine squared of theta. Well, tangent, we know we can write in terms of sine and cosine. So remember, tangent squared, then it's going to be sine squared. I'm going to go back to the x that I should have been using, and I somehow changed it to theta there. All right, so sine squared over cosine squared, all over, that's the same line as that one, okay? The sine squared that was on bottom. So we want to get rid of this cosine squared here, so we get rid of this little fraction. Multiply the top of the big fraction and multiply the bottom of the big fraction by it. So when I do this on top, I'm left with sine squared of x over, on bottom I have sine squared of x times the cosine squared of x. Sine squares cancel. We're left with 1 over cosine squared of x. And we know that 1 over cosine squared of x is secant squared of x. Guys, it's really important though on these, you got to show every single step, okay? I have to be able to follow you from the beginning to the end. Don't skip stuff, because if I can't figure out what you did, then you don't get the credit for it, because I don't know if everything went the way it was supposed to. You could have done something algebraically that didn't work and then double corrected yourself later to get that right answer. So you've got to show me every single step. All right, and then simplifying by combining fractions and using identities. So first, before we start this problem, let's think back. If I told you to take 2/3 and add 1/2 to it, how would you do that? Well, hopefully you're saying I'd have to have a common denominator. And so remember, one way to get a common denominator is to multiply each fraction by the other fraction's denominator. So I'm going to multiply this first fraction. I'd multiply its denominator by 2, and what you do to the bottom, you do to the top. The second fraction would multiply by that 3, the other one's denominator, and what you do to the bottom, you do to the top. And so then you would have like 4 over 6 plus 3 over 6. Combine your numerators. So 4 plus 3 over that common denominator to get your answer. Okay? We're going to do the same thing with trig functions. So if I want to subtract these, I'm going to multiply the top and bottom of this first fraction by the other one's denominator. So I'm going to multiply the bottom by the cosine of x and the top by cosine of x. I'm also going to take the second fraction and I'm going to multiply the top and the bottom by the other fraction's denominator. So I'm going to multiply both the top and the bottom by 1 minus sine of x. Alright, so what I'm going to do now is I'm just going to rewrite what I have. I'll make it one big fraction now, but I'm going to rewrite what we've got. Not actually going to work anything out except for to combine the fractions. So I'm just going to write it out. Cosine of x times cosine of x. Then there's a minus sign there. Then over here we have sine of x times 1 minus sine of x. All over our common denominator, which is just that cosine of x times the 1 minus sine of x. Now I'm going to start working in the numerator, okay? I don't want to multiply the denominator because most of the time something in that denominator will cancel. I mean, worst case scenario, if anything doesn't end up canceling, we can always distribute the cosine real quick as a last step, okay? So now let's go through this. And let's see, we got cosine times cosine, which is cosine squared. And then we're going to distribute this negative sine of x. So negative sine of x times 1 is negative sine of x. And negative sine of x times negative sine of x is positive sine squared of x. And this is all over that denominator. Remember, don't distribute this yet, okay? Now look in your numerator. Is there anything else you can do? There is. Remember, it doesn't matter adding and subtracting. The order doesn't matter how it's written as long as the sign stays with it. So I could actually rearrange this to put my squared terms first. So if I do that, I could rewrite this as cosine squared of x plus sine squared of x minus sine of x all over that least common denominator. Well, cosine squared plus sine squared, that's a Pythagorean identity, and it tells us right out, cosine squared plus sine squared equals 1. So I'm going to replace that. So this is 1 minus sine of x on top over my common denominator. Now remember, the 1 minus sine of x is super glued together because that minus sign, okay? So the only way you can cancel it is if you have a 1 minus sine of x on top and a 1 minus sine of x on bottom. And we do. So these two will cancel. Leaves us with 1 over cosine of x, which is a reciprocal identity. Reciprocal identity, which is secant of x. And so there is our solution there.